dear students, welcome to this program. Today we are discussing an important topic, that is fundamentals of organic chemistry first. The objectives are to understand introduction to organic chemistry, concept of hybridization of carbon, cleavage of covalent bond, electronic effects, structure and stability of reactive intermediates. Let's begin with introduction to organic chemistry. Organic chemistry originally was defined as the chemistry of those substances formed by living matter, and for quite a while there was a firm belief that it would never be possible to prepare organic compounds in the laboratory outside of a living system. However, after the discovery by Wöhler in 1828 that a typical organic compound, that is urea, could be prepared by heating an inorganic salt, ammonium cyanate, this definition gradually lost significance and organic chemistry now is broadly defined as the chemistry of carbon-containing compounds. Why is organic chemistry so special? Let's consider some of the factors that make so much of chemistry center on a single element, that is carbon. One very important feature is that carbon-carbon bonds are strong, so long chains or rings of carbon atom bonded to one another are possible. Diamond and graphite are two familiar examples, the diamond lattice being a three-dimensional network of carbon atoms, whereas graphite more closely resembles a planar network. Carbon is not unique in forming bonds to itself because other elements such as boron, silicon and phosphorus form strong bonds in elementary state. The uniqueness of carbon stems more from the fact that it forms strong carbon-carbon bonds that are as strong when in combination with other elements. For example, the combination of hydrogen with carbon affords a remarkable variety of carbohydrates or hydrocarbons as they are usually called. Now let's talk about hybridization of carbon. Hybridization may be defined as a phenomenon of mixing of atomic orbitals of nearly equivalent energy involving redistribution of energy to form new orbitals of equal energy known as hybrid orbitals. The number of hybrid orbitals is equal to the number of orbitals hybridized. The properties of hybrid orbitals are in between the properties of orbitals which are hybridized. Carbon is one of the most important materials and especially essential for organic connections because all organic structures include carbon. The atomic number of carbon is 6. Its electronic configuration in the ground state may be written as 1s2, 2s2, 2px1, 2py1 and 2pz0. According to this configuration, there are two half-filled orbitals. Therefore, carbon should be bivalent. But it is an established fact that carbon is tetravalent. Hence, in order to account for tetracovalency of carbon, it is suggested that one electron jumps from 2s orbital to 2pz orbital. Thus, electronic configuration of carbon in excited state may be written as 1s2, 2s1, 2px1, 2py1 and 2pz1. Carbon shows various types of hybridization which include sp3, sp2 and sp. Now let's talk about sp3 hybridization. The sp3 hybridization is the combination of 1s orbitals with 3 p orbitals, namely px, py and pz. 4 new hybrid orbitals are formed. The direction of orbitals and also the center of mass are determined by the specific contributions of the p orbitals and s orbital. The characteristic angle between hybrid orbitals in sp3 configuration is 109.5 degree. Now let's talk about sp2 hybridization. The sp2 hybridization is the combination of 1s orbitals with the 2 p orbitals, namely px and py. They contribute together to a planar assembly with a characteristic angle of 120 degree between hybrid orbitals, forming a sigma bond. The additional pz orbital is perpendicular to sp2 hybrid orbitals and forms a pi bond. A typical example of sp2 hybridized crystal structure is graphite. Now let's talk about some other types of hybridizations found in carbon. For carbon, the most important forms of hybridizations are sp² and sp³ hybridization. Besides these structures, there are more possibilities to mix different molecular orbitals to a hybrid orbital. An important one is sp³ hybridization, where one s and one p orbital are mixed together. The characteristic angle between the two hybrid orbitals is 180 degrees. Now let's talk about the cleavage of covalent bond. Bond cleavage is the splitting of chemical bonds. In general, there are two classifications for bond cleavage, homolytic and heterolytic, depending on the nature of the process. In homolytic cleavage or homolysis, the two electrons in a cleaved covalent bond are divided equally between the products. This process is known as radical fission. In heterolytic cleavage or heterolysis, the bond breaks in such a fashion that originally shared pair of electrons remains with one of the fragments. This process is also known as ionic fission. Heterolytic cleavage is most likely to occur in polar bonds, and the electrons will move towards the more electronegative atom. An example is the heterolytic cleavage of C-bromide bond in T-butyl bromide. Since bromine is more electronegative than carbon, the electrons move to the bromine. We get a tertiary butyl cation and bromide anion. Now let's talk about the electronic effects. Understanding the factors involved in the electronic imbalance is vital for understanding the basic mechanisms of chemical reactions. In chemistry, we come across these types of electronic effects: the inductive effect, resonance, Mesomerism, Electromeric Effect, and hyperconjugation. Let's talk about induction or inductive effect. Inductive effect is the transmission of charge through a chain of atoms in a molecule, resulting in permanent dipole in a bond. Covalent bonds can be polarized depending on relative electronegativity of the atoms forming the bond. The electron cloud in a sigma bond between two unlike atoms is not uniform. It is slightly displaced towards the more electronegative atom. This causes a permanent state of bond polarization, where the more electronegative atom has a fractional negative charge, that is delta negative, and the less electronegative element has a fractional positive charge, that is delta positive. Inductive effect of an atom or functional group is a function of that group's electronegativity, bonding order and charge, position within the structure. Now let's talk about resonance. Resonance may be defined as bonding or sharing of electrons between more than two atoms. Typical covalent and ionic bonding involves sharing of or the transferring of electron pairs between two atoms, as in ethane and sodium chloride respectively. In these examples, the bonding electrons are localized. Resonance differs from two other examples in that it involves the sharing of electrons between more than two atoms via delocalization. The classical example of resonance is provided by pi bonding system of benzene. Benzene is a six-membered ring composed of 6 sp² hybridized carbon atoms in a plane and sharing 6 pi electrons. It can be represented by Kikuel structure, which suggests an alternating single bond double bond bonding pattern. Now let's talk about Mesomeric effect. The Mesomeric effect in chemistry is a property of substituents or functional groups in chemical compound. The effect is used in a qualitative way and describes the electron withdrawing or releasing properties of substituents based on relevant resonance structures and is symbolized by the letter M. The Mesomeric effect is a permanent effect and operates in compounds containing at least one double bond and another double bond or a lone pair separated by a single bond. The Mesomeric effect is negative when the substituent is an electron withdrawing group and effect is positive when the substituent is an electron releasing group. Examples of negative M substituents include acetyl, nitrile and nitro. Examples of positive mesomeric substituents include alcohol, amine and benzene. Now let's talk about electromeric effect. The electromeric effect is an intramolecular movement of electrons from a pi bond to another atom in the molecule due to attack by reagent. It is temporary and reversible. There are two distinct types of electromeric effects. Positive electromeric effect. In this effect, the pi electrons of multiple bonds are transferred to that atom to which the reagent gets attached. The second one is negative electromeric effect. In this effect, the pi electrons of multiple bonds are transferred to the atom to which the attacking reagent do not get attached. Now let's talk about reactive intermediates. Most reactions in organic chemistry do not proceed in a single step, but rather take several steps to yield the desired product. In the course of these multi-step reactions, short-lived intermediates can be generated that quickly convert into another intermediates, reactants, products or side products. As these intermediates are highly reactive, they cannot usually be isolated, but their existence and structure can be proved by their theoretical and experimental methods. These intermediates are called as reactive intermediates. Examples of reactive intermediates include carbocations, carbene, free radicals, etc. Now let's talk about carbocations. A carbocation is a molecule in which a carbon atom bears 3 bonds and a positive charge. Carbocations are generally unstable because they do not have 8 electrons to satisfy the octet rule. The stability of carbocations is dependent on few factors. The first factor is to look at when deciding the stability of carbocation is resonance. Resonance is a stabilizing feature of carbocation because it delocalizes the positive charge and creates additional bonding between adjacent atoms. Decreasing the electron deficiency increases the stability. The second factor that should be considered when thinking about carbocation stability is the number of carbons attached to the carbon carrying the positive charge. We look at the number of bonding electrons that are attached to the carbocation because those bonding electrons will help in elevating the positive charge. Bonding electrons from adjacent sigma bonds may overlap with the unoccupied p orbital of the carbocation. This phenomenon is termed as hyperconjugation. Since the overlap supplies electron density to the electron deficient carbocation, we predict that increasing the number of hyperconjugative interactions increase the carbocation stability. Thus, increasing substitution increases stability. Therefore, the order of stability of carbocation can be summarized as primary, less than secondary and less than tertiary. Now let's talk about Carbanions. A Carbanion is an anion in which carbon has an unshared pair of electrons and bears a negative charge. The Carbanion exists in a trigonal pyramidal geometry. Formally, Carbanion is the conjugate base of carbon acid. A Carbanion is a nucleophile. The stability and reactivity of Carbanion is determined by several factors. These include the inductive effect. Electronegative atoms adjacent to the charge will stabilize the charge. Hybridization of charge-bearing atom. The greater the S character of the charge-bearing atom, the more stable the anion. The extent of conjugation of the anion. Resonance effects can stabilize the anion. This is especially true when the anion is stabilized as a result of aromaticity. Carbanions are trivalent with sp³ hybridization. The lone pair of electrons occupies one of the sp³ orbitals. At last, now let's talk about free radicals. A free radical is a species containing one or more unpaired electrons. Free radicals are electron deficient species, but they are usually uncharged, so their chemistry is very different from the chemistry of even electron deficient species such as carbocations and carbenes. The alkyl radical is a 7-electron deficient species. The geometry of alkyl radical is considered to be a shallow pyramid somewhere between sp² and sp³ hybridization, and the energy required to invert the pyramid is very small. In practice, one can usually think of alkyl radicals as sp² hybridized. Both alkyl radicals and carbocations are electron deficient species, and structural features that stabilize carbocations also stabilize radicals. Alkyl radicals are stabilized by adjacent lone pair bearing heteroatoms and by pi bonds, just as carbocations are, and the order of stability of alkyl radicals is tertiary greater than secondary greater than primary. With this we conclude today's lecture. Hope you understood. Thank you.